Log on, tune in, find out. Another good idea from Cambridge.
So, as for the last talk today, it's a pleasure for me to introduce Emanuel Winterfors, who represents the University of Edinburgh.
Partly, a little bit of Paris as well. I'm a student of Andrew Curtis, who I guess you're familiar with now. So yeah, it's getting a bit late and it's been a long day, so I'm going to try to keep it short and sweet. So I'm going to talk about Bayesian optimization in general, and in particular what advantages it can provide to the optimization parts of experimental design problems. Outline, I'm going to start off with talking a bit about traditional optimization approaches in experimental design, and a bit about the problems with those that a Bayesian optimization approach can remediate. Then I'll get in on Bayesian optimization itself, which is a fairly new field. There's not a whole lot of literature on it. So there are plenty of open problems still to seek your teeth into if you feel so inclined after hearing the talk. So the classical formulation of experimental design, I formalize it here as just choosing a particular design, xi, to minimize some sort of measure u of the expected uncertainty of the parameters post-experiment. Now, if you're to use a normal optimization approach on this, the problem with all optimization approaches is that you can never find the exact the exact optimum. Doing so would, in all practical cases, require infinite computation, even if you're just trying to optimize a simple function of one variable. You can get very, very close, of course, but you can never reach the exact optimum. And this, of course, gets a lot worse when the design criteria itself involves lots of computation. So for models that involve space and time dynamics, you typically have to solve or approximate partial differential equations, which if you want to have the exact answer also would take infinite computation. So you have to settle with some approximation, which the uncertainty of which poses problems for the optimization problem, because if you don't know what your exact objective function is, then it's obviously hard to find the optimum. And it can also be tricky to calculate gradients and other things necessary for most traditional optimization approaches. If you have a lot of noise on your objective function. So a lot of attention in the field of experimental design has been put on the objective function itself, the design criteria, how to define it in such a way that we can easily calculate it. So one uses the standard common approximations to linearize the model completely, or linearize it around particular values of the parameters of interest in some pseudo-Bayesian approach, while averaging over a prior on the model space. And somewhat less attention has been put to the problem of optimizing uncertain functions or noisy functions. There are some literature called on stochastic approximation, which can offer some help of getting convergence of an optimization algorithm for noisy functions, but the convergence rate is extremely slow. So what can Bayesian analysis offer? Well, the traditional Bayesian view is to have some sort of prior function of a space of parameters you wish to determine. Here it can be the whole shape of the objective function or just the value and location of the optimum, which relates to something that you can predict or calculate to make either an observation or just a computation of which the uncertainty is known, after which you can compute a posterior distribution, an updated state of knowledge of what the real values of your parameters are. So if you are to apply this approach to optimization, here your parameter is the whole shape of the objective function. So if this is some design criteria on a design parameter here, chosen just one parameter for visualization purposes, this function can of course take many different shapes and values. It can look like this, and if we look at the whole space of possible objective functions, we get something quite messy like this. Here I've just plotted them over each other. But if we do apply some prior distribution, or we have some prior knowledge of the characteristics of these functions, let's say we know that they're, like in this case, reasonably smooth, and they're limited in one range of design parameter, then we could visualize the resulting probability distribution, our prior on this functional space, as this marginal distribution. Here, the blacker it is, the higher probability. So here's one example of one such distribution where it contains lots of functions like here, but they've all been assigned a certain probability, which contributes a little bit to this gray mass. So if we can make observations or compute calculate approximations of the true functions here somewhere, let's say this blue line, if you can see it, is the true objective function that we don't know. We can compute some approximations to it that will randomly lie around this curve. So if we apply a Bayesian approach to this, each of the noisy approximations of this curve will contribute to improving the prior distribution on all these functions. So here I've added one noisy function, noisy approximation, which has improved, constrained a bit the prior around this point. We can add some more. Here's another one, further improving our approximation of what the true objective function is. And we can keep on like that. Here we've added maybe 8 or 10 different points, and already we have a fairly good, well, much better idea what the function looks like, even though the measurements or the approximations themselves are very noisy. But together they form a complete picture. So here I've added still about double the amount of approximations. So already here you can start at least having some idea of what the the global minimum of this design criterion is, if we want to minimize it. Now, one advantage, well, this has two advantages over traditional approaches. One is that the fact that the observations are noisy doesn't matter too much. All the information we have provided is completely taken into account in constraining the curve. And also we're not throwing away some old points in the beginning of the optimization sequence, as is often the case with non-global optimization approaches that will just converge towards one point. So we make optimal use of all the computation we have done. Here the points were just chosen at random, but we can of course view this as an experimental design problem where to observe or approximate the design criterion is by itself a design problem. So we could form some utility function here to minimize with respect to where we evaluate our next point on the curve. Here the utility criterion is the expected minimum of the curve. This fuzzy picture here will give us some ideas, maybe incorrect, of where the minimum is. So we want to try to improve our idea of how low the minimum is and where it is, of course, as much as possible. So after having made just one observation, here I've evaluated this design criteria to where to make the next observation, next approximation of the curve, which tells us that it's bad to do it in exactly the same place as the other one, but it seems to think that it's good here in the vicinity. So then it picked the minimum point to make the next observation here, which further constrains the curve a bit, and again picking the optimal spot for the next observation. One can, in that matter, construct a Bayesian optimization algorithm that will try to do the next function evaluation or approximation to maximize the gain of information of that computation. So here, yeah, it goes through a few more steps, and already it has found a fairly good candidate for one of the for the minimum, but that's a little bit lucky since it started near to it. And here it says that it's good to continue to evaluate further to gain further confidence on what the true function value is around this potential minimum it has found. Now, this approach can also be modified to perform optimal computation. That is, not only try to find the optimal spot to make the next function approximation, but also see how much computation should we throw into that particular function evaluation or approximation. If you, for instance, use some Monte Carlo method to approximate some integral on which the design criterion is based, the variance of the resulting estimate will be inversely proportional to the number of Monte Carlo samples. So of course the more computation you throw at it, the the more precise will the estimate be. But all computation comes at some cost. So a necessary concept then to try to find the optimal computational effort for each point is to assign some kind of cost to the amount of computation we're performing. It might cost $100 per week on a computer or whatever, and to be able to compare that to the cost or economic gain we can make by finding a better design. So by doing that, we transform the problem of just optimizing the design with respect to uncertainty of the parameters, rather to a problem of minimizing the cost of the uncertainty versus the cost of the computation. So by doing so, if you get another dimension to your parameter space here of where to evaluate a function and how much computation to throw into it, and you can try to find the minimum of that 2D problem. Or this approach, of course, works in more dimensions of the objective function. I've just chosen 1D for visualization. So. Now, there are quite a few not very well worked out aspects of Bayesian optimization. One obvious one is how to assign the prior to a functional space, since functional spaces are in general not just infinite dimensional, but it's not even countably many dimensions. So they're quite tricky to parameterize, and some good theory to guide in that process would be very useful. Another bit tricky aspect of this approach is that this problem of finding the next point to estimate the objective function is also by itself, of course, an optimization problem, which in the same logic ideally should be solved with a Bayesian approach. So you get a optimization problem within an optimization problem, but how do you choose the parameters of that Bayesian optimization problem? So you get, in the extreme case, kind of an infinite series of optimization problems to solve. And also in this case, I've just looked at the expected uncertainty reduction for doing the next observation. But of course, what we're really interested in is to minimize the uncertainty at the end of the computation. So ideally, you would need to look not only on the next approximation, but a whole sequence of future ones, which gets tricky because they all depend on the design or the place you chose to evaluate the previous ones. So it's an NP-hard problem in general, but from a Bayesian sense, even if it's very computationally intense, you can still do some calculation to gain some information on the expected final information gain. I think that's about it. The term, just to clarify, the term Bayesian optimization is currently thrown around a bit, since Bayesian is like the buzzword in some sciences, but almost all the algorithms that are presented as Bayesian optimizations do not work this way, with a notable exception of some work by a computer scientist, Nando de Freitas. I think he was represented at the previous DEMA conference here in 2008, at least his group by some PhD student. But they're unfortunately not here. But they've worked on similar methods for Bayesian optimization. But otherwise, typically what people call Bayesian optimization is a traditional optimization algorithm with some Bayesian element stuck onto it. Usually the genetic optimization algorithm with some little Bayesian feature. But it's not able to provide the same advantages as a fully Bayesian approach. Yeah, I think I'll end there.
Any questions?
I think the phrase which people bandy around in certain areas, maybe in control, is exploration versus exploitation dichotomy. So do you spend time optimizing, or do you spend time identifying the function? So it would be very nice if you or Luke or somebody around us came up with some real general principles for deciding the effort between these two things. Maybe Luke's going to do it in his talk, and yeah, the other point is in kriging. Of course, they do something similar. They krieg with. They do kriging estimates, which is essentially Bayesian, and they look at this expected decrease methods. So they place the point not where the maximum is, where they expect, where conditionally they expect the decrease in the increase in.
Yes, that's exactly what this criterion is based on. To clarify what the exploration, what was it, exploration?
Yes.
It's about is, should we spend the time computing the objective function, or should we spend time planning on where to compute it, or what parameters to select in that computation? And from the thought I've given to it, I feel quite convinced that the only way of tackling that is to assign some cost, or some way of comparing the goal of gaining information, reducing uncertainty, with the cost of computation. Because otherwise, well, all these there's no limit to how much computation these methods can eat. So you have to be quite stingy with your computational power if you're going to get anywhere with Bayesian methods.
Okay, Anatoly.
I haven't heard any references to people who spend their lives working exactly on this problem. And there are monographs, and there is a huge school in Lithuania, started with Mockus in the 60s and then 70s. And people like Zhilinskas, who is my collaborator on several books, and they spend all their lives just doing that. Not only them, there is a huge literature on this topic. Exactly all these questions are discussed in the 60s in all this. I'm not course of this on this particular topic, but it's their lives there, and I'm surprised you never mentioned any results on what they were doing, and they were discussing these problems, and they got around of this, and they have lots of models and all this Wiener process. Basically everything is known, Wiener process model, all these Bayesian computations can be done. Not multi-step, but one step. But they have around all these multi-step problems, and they have discussed these costs as well. And of course observations are noisy. And so I'm sorry, but I didn't hear any references as if it is a new topic, but it's been around for 50 years.
Yes, people have been doing Bayesian.
No, they did Bayesian, lots of Bayesian. They did lots of Bayesian. I know that because I'm co-author of these books, but it's not my chapters. And there is lots of material on all of this. So I don't understand how you cannot know these books and papers and not refer. Maybe you know, but you don't refer.
Well, the work I know most closely parallels what I presented here is that of the Nando de Freitas group is at University of British Columbia in Canada. But I'm sure there are older sources as well. He's also looked at the parallels to experimental design, since it's kind of an experimental design problem to choose the parameters of your computation function. I'm not aware of any completely general literature on completely general Bayesian approaches to optimization. Everything I've seen have been quite limited to a special class of objective functions or some very particular applications. But I'm very pleased if you can show me some.
I'll show you.
Some references.
Not really bad. No rush.
No, the Bayesian.
It's kind of fake, right?
The method called expected improvement is becoming more and more popular.
Well, it's the same
People
group.
doing, yeah, the same title, but it's doing like exactly that. I mean,
But Will Welch is a British guy. I mean, it's the same group, right? We're talking about.
and in
Yes.
fact they rediscovered a method that was suggested, as Anatoly said, in the 80s. But it's, I mean, this is all used at the moment. There are even some recent publications about instead of using expected improvement, where you're just looking one step ahead, trying to look 2 steps ahead, and using some approximations and so on.
Sure. You can improve slightly by looking a few steps ahead. What you really would like, of course, is to compute an estimate of the expected final design criterion after an arbitrary number of steps until some stopping criterion is fulfilled, so that the cost of computation exceeds the improvements that the computation can afford.
Yet another question? It seems to me that you wanted to ask.
Yeah, I mean, it may not be relevant, but I mean, I think the approach of Muller and his co-workers, where somehow you're treating the design as if you like, a random variable and sort of looking at joint posterior distributions, in some way is tackling this problem of avoiding evaluating a lot for designs that are going to be suboptimal, because it naturally is the posterior that will focus on regions of the space where the design is good. So.
Sure. Yeah, he's certainly done lots of work on Bayesian methods for experimental design. To my knowledge, he hasn't looked at Bayesian approaches to the optimization itself, but rather to cleverly evaluate the design criterion to make it less expensive.
Well, the optimal would come out as the mode of his posterior distribution. So.
Yeah. Well, if you do the full Bayesian thing with a prior on the space of objective functions, etc., then yeah, of course it's a Bayesian optimization
Mentioned it in my talk.
approach.
Thanks. Mario, please.
I wanted to ask, in this example you show, what prior are you using? Because you need a prior on a function
Yes.
space. Right?
I'm sorry about forgetting to mention that. So yeah, I can bring back the functions in slightly less messy form. So the prior I used here is representing the function by its Fourier decomposition, and putting an exponentially decreasing probability on high amplitude of high frequencies compared to low frequencies, which tend to make the curve smoothish, even though sharp turns are allowed, but not very high probability. It's a similar approach actually taken in image compression, for instance, like the JPEG format, where they do a kind of equivalent approach, setting a low probability to high spatial image frequencies compared to the low ones.
In some problems in practice, you actually have peaks in their singularities. Could have
Sure, sure. I mean, you have to, of course, adapt your prior distribution to the problem, the knowledge of the likely objective function you can get. And it's a generally quite tricky problem since functional spaces are so high dimensional, so it's quite tricky to represent them in some computational way that you can put into a computer.
Okay, thank you very much.